Okay.
All right, next piece. My favorite part, chaos. Uh, so we've got this picture of a low-level graphical model with some symmetry to it. Next up, we need to talk about sort of how high-level stuff, how it can make sense to talk about like high-level stuff existing in those models at all. And again, in like a universalizable way.
Yep.
So prototypical example I like to start with here is something like an ideal gas. So you've got a bunch of little balls bouncing around in a box. And this first observation is like this has both the locality thing and the symmetry thing going on, right? We've got these little balls are only going to directly interact with things nearby them. And we have a symmetry over time. The laws of physics are staying the same, right? Now, important thing about this system is it's chaotic. What does that mean? So at a certain time, you've got a state of all these balls, right? So for each ball, you've got some number representing its position, some numbers representing its position, some numbers representing its velocity or momentum. Right?
Yep.
So let's just pick one of those. Let's look at this one in particular. Let's say its velocity at like time 0 is represented by a bunch of bits. 0, 1, 1, 0, 0, 0, 1.
Okay.
And now the question that I'm going to ask is, okay, I want to predict something about the system later on. Let's say, for instance, I want to predict the position of this ball later on, or the position of that ball later on. It doesn't actually matter what.
Yeah.
So I'm going to be predicting some other number later on. And the question is, what information do I need about the first number in order to predict the second number? Now, this whole system, the laws of physics in this system are continuous. They're smooth. What that means in terms of like these bits is that if I only want to predict the first couple bits of, say, the velocity of that guy a little bit later, then I only need to know the first like 2 or 3 bits of the earlier velocity. So as long as I'm not looking very far ahead in time, something like this, and then to a good approximation, I can just like ignore the lower order bits. However, as I go forward in time, more and more of those bits become relevant. So if I want to predict the like first bit of the velocity of this guy later, or actually let's say position. Let's say I just want to predict whether this guy is going to be on this side of the box or this side of the box at some later time.
Yep.
Well, early on, I only need to know like the first bit or 2 of its velocity at the first time. Later on, I might need to know like the first 6 bits.
Okay.
Right? And if I keep going forward in time, then maybe I need to know the first like this many bits. And the further forward I go in time, the further back in this expansion I'm going to need to look. Whether this particle is ending up on this side of the box or that side of the box is going to depend on finer and finer precision in its initial state. That's chaos.
This is true on average. It's in principle possible that the first bit, in fact, requires the first bit one time step later requires all of the information from 99 bits back.
Correct. So, for instance, if this guy was starting out right on the line between these 2 halves,
Right.
then in that special case, this one would have to look a whole bunch of bits back.
Yeah. Or similarly, if it's like all zeros and you're like, what happens next, depending on the update rules. I'm not sure if that's the thing. That's what I would call this here.
Mm-hmm.
But like, if you're like carrying a 1 all the way through,
Mm-hmm.
Then maybe the 99th 1 through
Correct.
98 zeros makes a difference. But yeah, okay. But in general,
Key point with both of those examples is it can be more sensitive than this in special cases.
Yeah.
But neither of those allows it to be less sensitive.
Yeah. Okay.
So the key point here is, excuse me, conceptually, as we're running things forward, high order bits become more and more dependent on low order bits.
Yep.
And like the sort of lazy thing that we say then is that we're losing information about the higher order bits as we go. The reason we say that is because in practice, we always have finite precision on our measurements of the initial conditions.
Okay.
And this, importantly, this is a thing that's not just going to be true of humans. This is a thing that's probably going to be true even of like super intelligences. They're still going to have finite measurement abilities.
Yeah.
Right. And therefore, like...
I mean, I guess it's possible that the structure of the universe that you're in is, like, there just is only a finite number of bits.
Correct.
Like, if
so
you're...
the big way you can dodge this is if either our universe turns out to be like generated by a simple mathematical function, in which case eventually you figure out what the simple function is and suddenly you just know what all of the bits are.
Yeah.
Or the universe is sort of fundamentally discrete in a way where like there's an end here and you can just precisely know the entire state.
Right.
In that case, you would still have Maxwell's Demon style issues, so you still probably in practice wouldn't be able to do this for like most systems in the universe.
Okay.
Because like the universe is bigger than you, so it's hard to store the entire state in you. But
yeah,
these are the sorts of things that are potentially.
Okay, but you could do it for a particular. If one of those two possibilities hold, you could do it for a particular set of particles in a particular box.
Yes.
But you need a computer bigger than the box.
And you would also need the box to be like completely not interacting with the rest of the universe. Because if like a gamma ray comes in and flips one low order bit, then suddenly you have to account for that.
I see. And it actually has to be completely, because the whole point is that it's sensitive to very small changes.
And it does matter like how quickly it's sensitive.
Yeah.
In practice.
Yeah. So there's always good, because you have to model the whole universe. Like there's a limit to how far forward you can predict how the system will evolve.
Yep.
And if you're lucky and the things are fundamentally discrete, you could maybe in principle do this, but still only for a limited period of time before your random gamma rays or like some aliens moving, changing the gravitational effects or something, mess up one of your bits.
Mm-hmm.
Okay. Great. Okay. Chaos.
Yep. So that's like the conceptual idea of chaos. There's a flip side to this, which is in typical systems, it's not like all chaos. A typical case, there would be some conserved quantity. So, for instance, a discrete case, maybe we have this space I'm drawing is going to be like state space of the system. Maybe we have like a sort of line down the middle where like if your state is on this side, it's going to stay on this side and it will sort of chaotically wander around through all the possible states on this side, but staying over here.
Okay.
And if your state's on that side, it's going to stay on that side, but it'll like chaotically wander around through all the states over there.
Okay.
And then we would say that we have a conserved quantity, where that quantity as a function of the state is something like an indicator that's 1 if you're on this side and 0 if you're on that side.
Okay.
Quantity is conserved over time. Right?
Yeah.
The like classic example in basically in all physical systems would be energy. Like energy is conserved over time. And then you sort of chaotically wander around, subject to that constraint.
Yeah. Okay. Yeah. Our physical universe. So there's the state space of physical universes, and our physical universe stays in some subspace of that state space, which is the possible states of physical universes that have exactly this much energy.
Yes. And on in practice, on reasonable time scales, and looking at reasonably sized smaller chunks of the universe, we have more conserved quantities than just that. So for instance, you observe that this whiteboard is not immediately dissipating. It's sitting here, just staying there.
Yeah.
Conserved quantity.
Okay.
There are quite a few conserved quantities.
Although that's a lot. I could take a sledgehammer to it. That
and then it will stop being conserved.
Yeah, that conservation law is a lot less robust than
correct
conservation of energy.
Yep.
Okay.
So we've got conserved quantities. You can also have things moving in periodic orbits. That's a thing that can happen. There, you can sort of model that as a conserved quantity with a phase in there saying where in the orbit you are.
Okay.
Yeah, that's another possibility. Point is, typical systems are going to have some properties, some quantities which are conserved or periodic or straightforwardly predictable, non-chaotic. And then they're going to have some other quantities which are chaotic.
Just say that sentence again.
Typical systems are going to have some quantities which are non-chaotic, things like conserved quantities or things that are periodic.
Yeah.
And they'll have some other quantities that are chaotic.
Yeah. Okay. So there's some things that if you measure them, you know them. You know them reliably. Know them
reliably predict them well into the future.
Yeah, and there are other quantities that you're losing information over time in the sense that the limits of your knowledge at any time step become more relevant over time.
Yep.
Okay. So some things are so conserved quantities are sort of are non-chaotic features of your system. Okay. And everything's going to be either chaotic or non-chaotic. Chaotic or conserved. Are there other options?
So technically, periodic is a little bit different than conserved, but chaotic or non-chaotic is a reasonable way to split things. They're to the extent that there's a continuum here, it's because things can be chaotic on different time scales.
Yeah.
Something that's conserved on a short time scale can still be chaotic on a much longer time scale.
Okay.
Diamond does eventually spontaneously break back down to coal.
Okay.
Okay. So that's so far this has been sort of the classic dynamical systems way of thinking about chaos. Now we're going to push it a little bit further.
Okay.
I should get a picture of this. Erase it. Let's go back to our big old basements. I'm going to take a moment to draw a net with a whole bunch of arrows in it.
This does not look symmetric.
It is definitely not symmetric. The thing we're going to do immediately next does not require symmetry.
Okay.
So we've got you can imagine this sort of continuing off in whatever directions.
Yep.
This is going to be our decidedly not symmetric universe. At the moment, our universe exists in this giant basement. Now we need to introduce the idea of a markup blanket, aka a cut in this graph.
Yep.
So the idea is I'm going to slice through the graph, just slice through a bunch of arrows such that I cut the graph in two.
Yep.
That's a markup blanket. The idea is conceptually you can think of it as I'm viewing the universe as two pieces, and if I look at the states of all those arrows together, I can think of that as all the information that's flowing between the two pieces. In this case, I've drawn it so that all of the information is flowing from this side to that side.
Yep.
I could also draw one, say like this, where it's going both ways.
Okay.
The important point is just that I've sliced through all of the information that's flowing between the two.
Okay, so the first one you drew is a slice through time.
A time slice.
Yeah. And the second one is through space?
Space slice, yep.
Okay.
So the second one, an example of one that would look like that would be like I spatially split the universe in two along some plane.
But not in your... But...
And like each of these two halves is extending through time.
Yeah. And exchanging information back and forth.
Yep.
Okay.
Now, so far, when we've been talking about chaos, we've mostly been talking about things evolving through time. And that's the classic dynamical systems view, is the sort of thing that's chaotic is a bunch of states through time. So in other words, a bunch of these slices. So we've got like a sequence of time slices. The state of the Markov blanket, and each of those is just like state of the universe at a particular time.
Okay.
A little more degree of freedom than that, because we could take this slice to like not really correspond to a particular time. It's kind of funky to think of what it even means to think of a particular time across the whole universe because relativity, but like that's the idea.
The Markov blanket is a particular slice, or it's the space between two slices?
So the technical definition would say the Markov blanket is the random variables carried by each of these edges. So like if at each of these points I have some variable, like call that x, that y, that one z, sorry, not that one, that one z, then this Markov blanket would consist of x, y, z, etc.
Okay.
And then what I sort of like reason that's useful as a technical definition is because then I can say, all right, if I control for the values of those variables.
Okay. There's the last nodes before you cut the edges.
Yeah, because those are the nodes whose values are being carried by these arrows.
Right. Okay.
Right.
Right. So.
And then the reason that's a useful definition is because if I control for the values of those variables, then all the variables on this side become independent of the variables on that side. It's like these are the only interactions.
Yeah. Okay. So you can have a bunch of slices, which is the value of all of the nodes at a given time slice.
Yeah. Really, like a time slice is what it means to be at a time.
Yeah.
Yeah, and that's like the classic dynamical systems view of chaos is basically doing that. Usually they're also assuming that you have symmetry over time, which simplifies the math a lot.
Okay.
But that's basically what they're doing. We want to also think about sequences of Markov blankets over space. So things like... So now we've got like a sequence going this way.
Yep.
And we can talk about chaos sort of going this way rather than going that way.
Okay, where you're going to take a measurement of the evolution of a system through the whole evolution of a whole system on the left side.
It doesn't. You don't actually have to be measuring the whole system here. Remember, in like the example, the ideal gas example, what we're actually measuring is just like part of the state here, and then we're trying to make predictions about part of the state later on.
Okay.
Okay. Same thing here. So what we're measuring would be like, you go look at some part of the system at like for some amount of time over here in this part of space, like on this side of the room. And then I'm going to make some predictions about something happening on this side of the room. And then in between those, there's like lots of space slices. Like stuff has to propagate from this side of the room to that side of the room, right?
It doesn't propagate. That's still over time. If you have a time slice or if you have a space slice on at one time step.
Yep.
And then you want to know what's happening on the other side of the room at the same time.
Mm-hmm. You can still, so important distinction here. We're talking about informational interactions, not causal interactions at this point.
Okay.
Because we're saying like we want to make predictions about what's going on the other side of the room, given information about what's going on this side of the room. And information doesn't have to like follow causal arrows to propagate. I can have like, for instance, if I have two variables that are downstream of the same thing.
Yeah.
Like I've got a bias die and I roll it twice, so that both outcomes are downstream of the bias.
Yeah.
Then like observing this outcome tells me something about that outcome because they're both downstream of that same bias.
Okay, but not with extreme like you. So yeah, so if I look at one side of the room, I can make guesses about what's on the other side of the room.
Yep.
Because there's regularities. Like if it's really bright on one side of the room,
Probably really bright on the other.
right?
Yeah.
Because there's some connections between. Yeah, there's some similarities between what's happening on both sides.
There's some shared stuff upstream.
Yeah. There's some shared stuff upstream. But that's not necessarily the case. It can be the case that one side is really bright and the other side is dark.
Yep.
Because a boulder fell between them, and so one of them the shade of the boulder or something.
Yep.
And you're saying that's the same kind of thing as the chaos where you're like, I know the state of some part of the system at time step 0, and then at time step 100.
Yes.
I have guesses about how the system looks, but I can't. I'm losing information all the way.
Yes. In the case of like the ideal gas, assuming that your initial measurements were only about one part of the system, you are going to have just automatically some uncertainty about what's going on in some other part of the system at some other time. So you will be making probabilistic predictions there.
Okay. Yeah, so there are markup blankets. Markup blankets are going to look like, we have markup blankets that are approximately slices through time or approximately slices through space.
Mm-hmm.
I imagine you can also do a markup blanket that is cutting diagonally.
Sure can.
So
you can do all sorts of crazy shit. You want to make like a little ball, that's fine. You cut out like a ball of space-time, that's fair game. You want to make a markup blanket that goes like this, that's a totally valid choice.
Okay.
Cut these things up however you like.
And why do I care about markup blankets?
So the reason we're introducing them now is to introduce this idea of like a sequence of markup blankets.
Yeah.
And then you have chaos that instead of operating over time, like you're losing information over like time 1 versus time 2 versus time 3 versus time 4, instead you're losing information from like chaos-like phenomena over markup blanket 1, markup blanket 2, markup blanket 3, markup blanket 4.
Okay.
And it's for the same reason as like chaos in general, is because like in lots of systems, as you move from like markup blanket 1 to 2 to 3 to 4, you're trying to make predictions, it's going to become dependent on lower and lower order bits.
Okay. You numbered the markup blankets, although where you draw them is arbitrary.
Mm-hmm.
Especially if the it can be the case that there's one arrow on one side of the graph, or one edge on one side of the graph, and then a series of 3 edges on the other side of the graph, and you have to decide where to cut it.
Yep.
I guess you could make a markup blanket after every edge.
Yep. So this is a place where we want to be setting things up so that the things we're saying don't care that much about which markup blankets you pick.
Okay.
The thing that we're using these markup blankets to do, or the thing that we want to use them for, is to say like, look, in the underlying system, there's going to be a bunch of information loss because of like chaos type mechanisms. And regardless, if like I'm able to use this sequence of markup blankets to say, okay, most of the information is being lost between here and here, then that's still going to be true once I forget about the markup blankets. It's sort of an underlying fact about the universe that I have very limited ability to predict this guy from that guy. And I'm using the markup blankets as a tool to establish that, to talk about that.
Okay.
Make sense?
I think so. Yeah. All right. What's next?
All right, let me check my notes. So with that under our belts, we can again talk about when you're talking about the ideal gas, for instance. We were saying, well, there's going to be these conserved quantities, and these are things where even a superintelligence is not going to be able to do like very good prediction except for the conserved quantities.
Yes.
Case. Now we want to generalize that to this picture. Say that doesn't just apply to things over time, that applies to things that are spatially separated, that applies to things that are far apart in general in a graph. Like if they have lots of layers of Markov linkage between them, there's going to be an opportunity for chaos to kick in. And then, like, there's going to be a method of predicting that's analogous to, for instance, maximal Boltzmann statistics for the ideal gas, where like you're controlling for the conserved quantities, everything else is chaotic, and then that's just like the best prediction you can get, unless you have like exactly perfect information about the system. So there's sort of this low ceiling conceptually on how good your predictions can be. Does that make sense?
Doesn't that depend on how far in the future you're predicting?
Correct. However, it's so the typical case once we add symmetry back into the picture is going to be exponential loss of information at an exponential pace. So like it will sort of in a quantitative sense depend on that, but qualitatively it's going to drop off real fast.
Okay.
There will still be a difference between like very different timescales. So again, there will be different conserved quantities on a timescale of like 2 seconds versus 2 years.
Yeah.
But that's the basic idea.
Okay.
So in that sense, we get these quantities that are sort of natural things to like think about. We get sort of these natural high-level quantities like energy/temperature for an ideal gas, or whatever else is conserved over time or space in any particular system.
The high-level features, I'm not sure I follow that. The high-level features depend on the time scale?
Yes. So, for instance, this comes up a lot when talking about chemical reactions, for instance. Sometimes you'll have, any given chemical reaction has a certain rate to it, a certain rate constant, and some reactions happen a lot faster than others. So if have like 2 chemical reactions going in a little beaker, then maybe one of those, if I'm looking at it on a time scale of 1 second, maybe one of those reactions is going very quickly, so like concentrations of its reactants and products are changing, but the other one's going very slowly, so its reactants and products are roughly conserved. But then if I let it run for an hour, both of them will change.
Okay.
Or similarly in an organism, like looking at cells in my body, right? Something like proteins will turn over on a much faster time scale than cells. So if I'm looking at like, well, where is there a particular cell, that's going to stick around for a lot longer than most proteins will.
Okay.
Yeah, so different time scales.
Okay. Would you basically say that different things are like have different levels of robustness?
Bingo.
And some things are more robust than others, and we're calling the robust things conserved on the time scale under which they're robust.
Yep.
Okay.
And then similarly over space, some things are sort of more spread out over space. Some like quantities are more conserved over space. Would be a good example of that. If I think about like the pressure in this room, if I go measure it way over there, I'm going to get basically the same measurement that I get over there.
Okay.
If I go wandering all the way out to Mercury, I'm going to get something very different.
Yeah. Okay. Great. So we have the causal. Not necessarily causal. This is a causal graph, but there's informational. You don't have to follow the arrows you can infer information from other parts of the graph instead of by backtracking. You don't have, such that it is a like directed causal graph or an undirected informational graph. And then we can take Markov blanket slices, and there's a state at any given time, and there's sort of chaos both going in space and in time, and in more generally just between Markov slices.
Yep.
Okay.
All right. Time to talk about why we needed all this machinery.
Yeah.
So the very next thing we're going to talk about is going to be very simple organisms. So
Okay.
beginnings of biology, things that can self-reproduce.
Okay.
And then we're going to want to say something like you've got some sort of pattern, like some little cell here, that's A, surviving through time.
Yep.
Wandering around, and B, making copies of itself.
Okay.
Right? And then we need to say, okay, what the heck does it mean for like this thing embedded in this physical system to be making a copy of itself? What does it mean to say that like this thing here at this time is a copy of that thing there at that time, or this thing here is a copy of that thing there at that time, right? This is the machinery we're going to use to do that.
Okay.
So first of all, let's set up like why this is sort of a tricky question in the first place. Cells notoriously turn over all their constituents, so it's certainly not like these guys are made of the same molecules, right?
Yeah.
Even before we get down to the level like quantum mechanics or whatever, if we're just looking at particles, they're made of different particles.
Yep.
They're not going to be like exactly the same at any level you look at them. There's going to be some mutations in the DNA. They're going to have slightly different shape. Like everything about them is going to be slightly different, right?
Okay. Although they're similar to each other.
And then the question is, in what sense are they similar to each other? So the sort of problem that I have in the back of my head here is, imagine I had a computer program that was just like low-level physics, doing this stuff, right? How do I go into that simulation and ask like, hey, are there any patterns in here that are reproducing themselves, right? Are there any things doing this?
Okay. And it seems like to do that you need to sort of like draw a boundary about which things count as like this cell. As it's like wheeling around or whatever.
Yep.
And then you could be like, and then you could count them. Then you're like, there's this cell, and now there's two of this cell.
Yep.
Is that hard? Can I?
So once we get to the point of being able to tell, like, there's a cell here, yes. There's a cell there, no. There's a cell there, yes.
Yeah.
Then it's pretty easy. It's that problem of being like, yes, there's one here, no, there's one, no, there's not one there. That's sort of the hard part.
I have a big causal graph, and then I want to identify, like, so first and foremost, I'm just trying to identify objects. And objects are going to be things that are conserved on some time scale, or there are some properties that are conserved on some time scale.
There's a little bit more to objects than that, but that's going to be like the main building block. We're going to get to that shortly.
Objects.
All right, if you're double clicking on this, then I think we should pause the video here, take a short break, and then restart.
Okay. Are there more questions that I should ask here? I'm like, okay, so the overall summary is you're like, you have a big causal graph. There are some things, it's not just proof cells, there are also like rocks and stuff.
Yep.
You're maybe like less interested in like, is that the same rock or something, but you're like, here's a rock, and then 2 time steps later, or 2 Markov blankets later, there's also a rock.
Yep.
There are a bunch of, you can tell because the particles, are like roughly in the same shape.
You can take your rock and look at it with a microscope and see that it has like all the same little defects in there at the 2 temps.
Yeah. Which I guess in your causal, not actually sure how that's represented per se in the like causal graph. I guess it's just like there are nodes where like these particles are basically in the same state, or also they move together. Like if I pick up the rock, they all move.
Yep.
They all move at the same time.
That's the right idea.
Yeah. So okay. So there's like a list of regularities that, or I don't know if I want to call them regularities. There's a list of properties that objects have, such that you can identify them in the causal graph, like that. Maybe this is like, then you also maybe want to talk about fluids and gases, but like starting with
Rigid body objects are the easiest starting point.
yeah, there are a bunch of low-level features which remain the same between different Markov blankets.
Yep.
And then also they all change at once. The term for each of the particles' elevation changes. They all change by the same factor. I guess unless the buck is rotating.
You can pretty easily extend that story to talk about rotation.
Yeah. Okay. And so so that's what objects are. You need some amount, so it's going to be fuzzy, given that molecules are bouncing around a little bit. They're bouncing around a lot more in cells than in rocks.
Yep.
So, like in cells, everything's like squiggling around. The ribosomes are doing stuff. So you have to identify more specific regularities than just like all the defects between the rock molecules, and be like, well, the key thing about the cell is that there's a membrane. Probably
there's a whole bunch of key things.
Yeah. I think if you're playing the game of being like, this is the essential characteristic, and if it has this, then I call it the cell, and if it doesn't, then it doesn't. It's probably a losing game.
Yep.
But you have a cluster of characteristics, and then you could give you look at like some spot on the causal graph, and you're like, give this spot on the causal graph a score based on how much it is this cell.
Yep.
Or a cell, or this specific cell.
Yep.
And you're like, most spots on your universal causal graph get like super, super low, and some of them get pretty high. And the ones that are pretty high, those are the cells.
Yep.
What's the problem with that basic outline? Does that just work?
Yep, you got basically the right idea there.
Okay.
I'm going to flesh it out a bit more. But
Great.
Yeah, basically the right idea.
Okay.
All right, I do want to pause the video there.
All right, yeah. I'm going to go to the bathroom.
Me too. Can you pause that?
Oh, right. Only my
Only your
my fingers can open the